Okay, so today we're going to finish up in this video the 2.2b notes, and we're going to talk about the domain of a function. So the domain of a function are always the x values of the function. When you're reading it on a graph, it's going to be all the points from left to right. So when we're talking about a domain of a function, it's always going to be all real numbers, except when there's a variable in the denominator. And when that happens, we're going to set the denominator not equal to 0 to figure out what x can't be. Also, if there's a variable under a square root, we're going to set what's under the square root greater than or equal to 0. And then that would be the numbers we exclude. And also if there's a variable under a square root when it's in the denominator, that's when we would only set the denominator greater than 0, because it can't equal 0 when it's in the denominator, because that would make it undefined. So let's just try an example of finding the domain of all of these functions. So when we do this, we're going to find the domain and we're going to write it in interval notation. The only one that we're not is the first one, because it's just a set of numbers here. So remember, the domain is always your x values. So the domain here is super easy. You're just going to write down all of the x's. So 3, 4, 5, and 8. The range of this are all the y's. But again, we're only talking domain here. Now, whenever your function, if it does not have a square root or if it doesn't have a fraction, the answer is automatically all real numbers. So you're going to write from negative infinity to positive infinity. The only time it's not going to be this answer is when there's a square root or if you have a fraction. Other than that, it's always all real numbers. The next one is the same thing. No fractions. Well, there is a fraction, but there's no variable in the denominator. So that's when we would have to check, is if we have a variable in the denominator. So this one is also all real numbers. Same thing for the next one. No square roots, no fractions. So this one also is all real numbers. Same thing for number 5. No radicals, no fractions, all real numbers. Boom, we hit a fraction. Okay, what number is going to make that fraction become a 0 in the denominator? A 0, right? So what's going to happen here, and we're going to write it in interval notation. So what you're going to do whenever you have a fraction, and if there's a variable in the denominator, you set that denominator not equal to 0. So in this case, it's just x. So x cannot be a 0. So what we're going to do, it's going to be all real numbers except 0. So the way that we'll write this would be from negative infinity up to the 0. It can't include 0, so that's why it's a parentheses. And then we're going to start up again at 0 and go to infinity. So if we looked at this on a graph, what would happen here is on our graph, this would be an open circle, and then it would be the rest of the graph. So the open circle is where the U goes. And notice there's parentheses around the zeros because it goes straight up to the 0, and then it can't include that, so it stops there, and then it jumps over that 0 and keeps going. And the reason why we put 0 in our interval notation is it could still be 1/2, and that would be a good value. So that's why I don't want to put the next integer. I have to put the number that's excluded. Let's try the next one. We got another fraction, but this time we've got an expression in the denominator. So we got to figure out what number x cannot be, and the way that we find that is setting the denominator not equal to 0. I'm going to solve for x. X cannot equal 5. So it's all real numbers except for positive 5. And again, I got to write it in interval notation. So from negative infinity up to positive 5, and then it stops and jumps over 5, and then it starts up again. So it'd be like a hole in your graph. Going to do the same thing on number 8. It's a fraction. It's got a variable in the denominator. I need to set the denominator not equal to 0. So 2x plus 1 cannot equal 0. If it does, then it's undefined. Subtract 1. 2x is not equal to negative 1. Divide by 2. And x cannot equal negative 1/2. So again, in interval notation, it's going to go from negative infinity up to the negative 1/2, jump over it, start up again, and go to infinity. So it's all real numbers except when x equals negative 1/2. Going to do the same thing on the next one. Set the denominator not equal to 0. So x squared minus 1 cannot equal 0. I can either factor this or I could do square root method, either way. If I move this over, then I square root it, x cannot equal plus or minus 1. We could have also, instead, we could have said x minus 1, x plus 1, and then set each factor equal to 0. Just remember, it's both. Now, this one's going to have a bunch of parentheses because on my number line, it looks like this. There's a hole here at negative 1 and positive 1. So then it really goes here in the middle, and then it keeps going here. So it's stopping here. So this interval notation would be from negative infinity up to the negative 1, then the red hole there where negative 1 is, and then it starts up again, negative 1 to positive 1, and it's got the hole where the negative or the positive 1 is to infinity. Let's try some radicals. Over here, this one, when I do this one, x squared plus 4. When it's a square in the bottom, I don't have to worry about any negatives because this can't be factored. So it doesn't matter what's going to go in here. This will always be positive and it'll never be a 0. So this is all real numbers. Because if I try to solve this, I get an imaginary. And I don't want to have to worry about excluding imaginary numbers. This would give me x is not equal to plus and minus 2i. I'm only talking real here. Now, when it's a radical and there's not a fraction, what we do is we take what's under the radical, not the radical, and make it greater than or equal to 0. Because we don't want the number under here to be negative. We don't want a negative number, so that's why greater than or equal to 0 is positive. So this would mean that the domain here is going to be from 0 to infinity. When it's greater than or equal to, it gets a bracket around 0. Over here, same thing. Set this greater than or equal to 0. So x is greater than or equal to 3. So a bracket around 3 going to infinity. So for the next one, I'm going to go ahead and do the 15 first. So whenever the radical's in the denominator, I'm going to set it only greater than 0 because I do not want it to equal 0. So this will just be 0 to infinity with parentheses. Over here, 2x minus 1 greater than 0, 2x greater than 1. So x has to be greater than 1/2. So parenthesis around half, going to infinity. Okay, so let me just go back up here and do 13 and 14. So again, it's under radical, but this time it's not a fraction. So what's under here we don't want to be negative. So we're going to set 2x minus 1 to be greater than or equal to 0. So 2x is greater than or equal to 1. Divide by 2. And x has to be greater than or equal to 1/2. So again, in interval notation, because it's got the greater than or equal to, a bracket around 1/2 going to infinity. Same thing here. What's under here has to be positive, so greater than or equal to 0. This time I'm just going to add the x. So 4 is greater than or equal to x. If you want to flip it around, just make sure Mr. Alligator is still eating the same thing. So again, this is a less than or equal to. So from negative infinity up to the 4 with a bracket around 4, but a parenthesis around infinity. We have 3 more examples, numbers 17, 18, and 19. So this time we got double stuff here. So we've got radical in the numerator, radical in the denominator, so it's going to be where both of them are true. So again, for the radical in the numerator, x minus 1 has to be greater than or equal to 0. And then for the denominator, x plus 2 only greater than 0, because it cannot equal to 0 in the denominator. So I'm going to add 1. X must be greater than or equal to 1. And then here, subtract 2. X has to be greater than negative 2. So really what I want to do here is, let's give myself a visual. So if I put it on a number line, so for the first one, let me just add in negative 2, negative 1, 0, 1, 2. So for the first graph, let's do this one in red. So this will be a closed circle on positive 1, going this way, and then this one, open circle right here, going this way. Now I only want where I see both the red and the blue. So from this point on is my answer. So it's going to be from 1 to infinity. So it has to be where both of the checks that we have done are true. So let me go ahead and do the next one. 2x minus 1. Again, it's in the numerator under a radical, so greater than or equal to 0. The denominator, just make it greater than 0. So I'll solve this one. Divide by 2. X has to be greater than or equal to 1/2. Do this one. Subtract 3. X needs to be greater than negative 3. And again, let's put it on a number line to see where they're both going to show up. So negative 3, and again, I don't need to put in all the numbers. I know positive 1/2 is here. So if I graph this one in red, it's going to be a closed circle on the 1/2, pointing this way. And then for this one, it'll be an open circle going right here. And again, I want where I see both red and blue. So the final answer here is going to be from the 1/2 to infinity. Notice the 1/2 has the closed circle, so that's why it has a bracket. Going to do the same thing on number 19. Again, I'm going to set the numerator to be greater than or equal to 0. And for the denominator, x squared minus 81 has to be greater than 0, because it can't equal 0 in the denominator. So here I'll add 1. X has to be greater than or equal to 1. And then over here, what I'm going to do is factor this, x minus 9, x plus 9, and greater than 0. So then x is going to be greater than 9 and greater than negative 9. So again, let me go ahead and add all this information to my number line. -9, +1, +9. So let me go ahead and graph each of these. So for the first one, I could do in red. So it's a closed circle on +1 going this way. And I'll do this one in blue. So this one's the open circle going here. And then lastly, let me switch the color. I'll do purple. And again, over here, open circle going here. So again, I only want where I see all three colors. So I can see all three colors right here. And notice the open circle on the 9. So this is going to be a parenthesis around 9 going to infinity. And this would be the only x values that are going to be greater than 9 that will work into this problem and not make it undefined or not give me a negative number under the radical. So that concludes the notes on 2.2b.